Hi everyone. Today we're going to talk about the upper and lower bound test for the real zeros of a polynomial. This test can, as you can see, this test can help show if a polynomial will have a real zero beyond a certain value of x. So we call it an upper bound or a lower bound. It means the zeros do not exist beyond that boundary point. So here we're going to show that 4 is an upper bound of the following polynomial, and we're going to do it by doing just synthetic division. Okay, so we're going to put 4 as our divisor, and then we're going to put our coefficients in, -1, 2, 3, and 1. And when we do this synthetic division, what we're looking for is what we're really going to just pay attention to are the coefficients of the division. So of course we bring down the -1, and 4 times -1 is 4. All right. -4, sorry. Then we add, and that's -2. Then 4 times -2 is -8. And we add, that's -5. And then 4 times -5 is -20. And then we have our remainder here of -19. Now I want you to notice something here. Notice how every single coefficient of of the quotient here and the remainder have all the same sign. So what that tells us something about our, I want you to notice that there are no sign changes in the the coefficients. And this proves that 4 is an upper bound. So what we're really looking for in the synthetic division is no sign changes among all the coefficients. So if it starts as a negative, everything else should be negative. If this was a positive leading coefficient, then every other coefficient and the remainder should then be positive as well. Okay? So let's look at another example of this. Let's do, show that 3 is an upper bound of this polynomial. Okay? So again, we do our synthetic division operation. 4, -6, -7, 9, and 2. Okay, we'll list all our coefficients and we begin our division. So 4, then 3 times 4 is 12. That gives me a 6. 3 times 6 is 18. That gives me what, 11? 3 times 11 is 33. And we add again, that gives me, 47. Then 3 times 47, well, I have to do this in my head, so that'd be 141. And we add again and get our remainder of 143. Notice no sign changes among the coefficients. Every coefficient has the exact same sign. Therefore, 3 is an upper bound. Okay, what that really means then, if you think about it, that means then this polynomial has no zeros above the value of 3. Above the x value of 3. So you couldn't expect 5 or 10 or 20 to be a real zero of this polynomial. And notice that's real zeros in the definition, not imaginary zeros or complex zeros. But real zeros do not exist above the number 3, above x equals 3 on the graph of this polynomial. Okay? So let's see if we can, let's move on to the next example. Okay. Now we're going to talk about, notice, the lower bound. And the lower bound test is just as simple as the upper bound test. You still do the same exact process of synthetic division. So we're going to do -1. Okay. Now some math teachers and mathematicians may argue what I'm going to show you is not the true lower bound test. But I've found it's just as effective as what some would define as the true one. And I'll show you what I mean here in just a moment. Now, if we were going to follow what some would say, you'd have to reflect this over the y-axis and then use the opposite of this to prove that this is a lower bound. But a technique I'm going to show you now, you don't have to do that. You just have to do standard synthetic division with the sign of the root you're trying to prove. So we do 3. -1 times 3 is -3. Okay, then we add, we get -7. Then -1 times 7 is 8, and that gives us 9. Then -9, and That, of course, gives us a remainder of negative, what is that, negative, what? Oh, I made an error, didn't I? Oh, typo, typo. This should be a 7. So let me just redo that real quick. Okay. Wow. My brain just dumped here. Okay, so negative 1 times negative 7 is 7, not 8. So that adds together to be 8. And this becomes negative 8. And then we get negative 5. Okay, so notice here. Notice that the signs alternate. Okay, the signs alternate. And that's a big deal because what that tells us here, okay, is that the signs on the coefficients, since they alternate, it actually proves that negative 1 is a lower bound. So when you do this test, when you do synthetic division, if you notice that the signs of the coefficients in the quotient are alternating, you know that that value that you're working with is a lower bound of the polynomial. So there are no real roots that exist below negative 1. And that can be very helpful when you're trying to find the zeros of your polynomial to know you don't need to look any further below that. Okay? So now we're going to show that 5 is a lower bound of this polynomial. And it works exactly the same way. Okay? So we say negative 5. Okay? And then we draw. So we put our information on our coefficients. And then we do our division. So bring down the negative 1. The negative 1 times 5, of course, is 5. And that becomes 9. The negative 5 times 9 is negative 45, which gives us negative 52. Okay. And then negative 5 times 52. Negative 5 times 52 is 260. And then we add again and we get 262. So if you take a look at this, notice that the signs alternate. And since the signs alternate, we can say that negative 5 is a lower bound. Okay, well that's it for today. Thank you for watching. If you, and we'll see more later this week.